Hello people, so my name is Josh. I was a computer science examiner for multiple exam boards, head of computer science in UK based schools, and now I run a tutoring business. I've been trying to get out loads of content for you because I know that paper 1 is coming up on the 10th, so I'm trying to get as much stuff out there as possible for you. Today's lesson is all going to be to do with systems architecture, and the way that I see it, in that we can still reasonably affect what grade you're going to get, is by remembering a load of definitions. Why do I think that is? So I use my examiner knowledge and the mark schemes, and I've been analysing them, looking at them, to give you the exact definitions that you need to remember for this. So I've just gone through as many spec points as time allows for, and given you all of the questions that could potentially come up, and then essentially I've just given you the answers. What I would recommend doing, the way that you're going to get most out of this, is if you make a flashcard per question, practice it until you can remember it without, obviously without looking at it. And that then means that when you get, if any of these questions are to come up, you have got some kind of talking points with them. The way that these are marked is that you get knowledge points, application parts, and then for the longer style questions you also get what's called an AO3 mark, which is evaluation. You don't really need to know all of that, but I just want you to understand the thought process behind this, is that if you know the knowledge points, that is something that we can tangibly affect in a very short period of time. If you make a load of flashcards, go through the other videos as well, it is the quickest thing that you can do to affect to get a better grade, because it's easier to learn definitions. You get some flashcards. All I'm thinking is just go through them for like 20 minutes until you can remember them. Go away from them, and next have a break, then 20 more minutes, and then do them again. And if you do them 2-3 times a day, so today is Friday, Saturday, Sunday, you're gonna be able to remember that. And that isn't even like a large period. That's an hour out of each day, and then obviously you're going to be doing other revision and things like that in that time. So I think it's a really, really easy way that we can actually grab a couple more marks, which could be the difference between, you getting a C and a B, or an A and A star. So the grade boundaries are low, people. The grade boundaries are low on computer science because people find this qualification very, very difficult. So I've tried to do as much stuff on systems architecture as possible. This is going to be for all specifications, but for OCR, what I'm going to do is I'm going to add in a little extra. I'm going to do an assembly code 1, AQA. If I've got time, I will try and get some assembly code stuff out for you as well, because there is actually a slight difference between the two of them, and Cambridge International as well. We'll see. I'll see what I can do. So anyway, let's get the definitions done, because that's going to be the easiest thing to do. So, okay, von Neumann architecture. The A-level definition for this is a CPU that has one bus and one memory location for data and instruction. That's the first point. So it's just that they're stored in one place. It also has a control unit, and an ALU is another point. It fetches, decodes, and executes instructions from RAM. So there's probably a little bit more than what you need there, people, but those are the points that I would use. Harvard architecture is where you've got a processor that has separate storage spaces and buses for data and instruction. So data uses its own individual bus. Instructions has its own individual bus, and they all have their own memory locations. Because of the sort of application points now, so Harvard architecture is normally used for quite high processing embedded systems. The reason for this is it's actually quite a complicated program, a complicated system to work. So they need to do it with simpler tasks, but it does allow for essentially you don't suffer from bottlenecks that you would get in von Neumann, because you have got the two separate buses. So those are some application points that you can use there. Purposes of individual components of the CPU. ALU performs mathematical operations. Everyone remembers that because arithmetic, but then they also forget to put in the logic gates. That's how you get the second mark. Control unit does the decoding and executing part of the FDE cycle, sends control signals to other parts of the CPU. Cache stores frequently used instructions so that you don't have to go to RAM to fetch it. Different buses within the CPU. I have no idea why they like to know this when you're describing them. So the three of them, you'd get a mark for just stating them because they'll be like state and describe a bus. I've put them all there for you, so you can make a flashcard for each of those. Control bus, 1 mark. I don't know why they like to know about whether it's bidirectional or unidirectional. So data and control buses are bidirectional. Address bus is unidirectional. Control bus essentially sends out control signals to the input and output devices and main memory. Also receives data from them. The idea of that being bidirectional. Data bus, just remember that it does data and instructions. Address buses send the addresses and retrieves them from the processor. Okay. The specific registers. Now, if they would just get you to state and describe them, the three that you need to know 1, 2, 3, 5. Sorry, I don't know why I said 3 there, but yeah, you need to know 5. The point with these is if you can just remember one sentence about these. Okay, so it's holds the address of the next instruction to be executed, program counter. Holds the address of the current instruction being executed, memory address register. Holds the data that is currently in use by the CPU. Holds the result of any calculation done by the ALU. And then the current instruction register holds the instruction that currently being executed. Okay. I know that sounds really, really confusing, and at A level you are starting to get a bit more familiar with this stuff because I'm hoping that you've done some of the assembly code stuff. If you haven't done any assembly code stuff for whatever reason at school, I am going to show you how that all fits together. But what I've tried to do is use my knowledge of looking at the mark schemes to give you as little as possible to remember, and you still be able to grab a mark on this. At A level, they would probably be a second mark attached to this, and I'm going to show you how to get the second mark. But the way I've tried to make this more simple is, can you see for program counter it says holds the address of the next instruction to be executed, and then memory addresses holds the address of the current instruction to be executed. The definition is very similar. The only difference is one is current and the other is next. So one definition, you change one word and you still get the marks for it. Memory data register holds the data currently in use. So only word there that's changed is data. So again, 3 definitions. Three definitions, but you only use one. Current instruction register holds the current instruction being executed. So again, you just change instruction. I've put in the other little extra points as well in case they give you a 2-mark question in there as well. So program counter increments after the data is passed to the MAR. Second mark there. Memory address register receives address from program counter. Second mark. The accumulator is where data decisions are made from. Where branching decisions are made from. When we look at assembly language, well, this will make a little bit more sense, but you use things like BRZ, BRA, BRP. That is essentially how you create decisions happening there and loops and in assembly language. The accumulator is where that decision is made, so that's kind of a little extra point. The other one is input and output device. Input and outputs come from the accumulator. The current instruction register is it splits into operand and opcode. If they wanted a second mark for the memory data register, I would say that when it fetches the data from the CPU fetches the data from main memory and brings it back to the CPU and stores it in the MDR. I have no idea why this was such a big thing, but I remember when I was marking one of the papers, and you'll notice that I changed the way that I said that, which was all to do with these are just memory stores. We weren't allowing marks 1 year. This may have changed now, but we weren't allowing marks 1 year if there was an inference that the registers were like doing any of the passing. So can you see? I haven't said the program counter passes the data to the MAR. All I'm saying there is that the data generically is passed to the MAR, and you're probably thinking that this sounds absolutely mental. Like, why am I going into so much detail on this? They are just memory stores, and the thought process behind this was the CPU is doing the passing of the data. These are just storing the data, and it sounds ridiculous now that I'm saying this sort of out loud, but we weren't allowing marks on one and then the other. I didn't make the decision, but it's just I do remember that. So just making sure that you're not saying like the program counter passes the data to the MAR, or the MDR gets the data from the RAM. It's the CPU which does that. I know that's a little sort of, if that sounded a little bit confusing, just get these definitions down. That's the most important thing. More of an A-level thing as well is the idea of the FDE cycle. So you need to know what the registers are doing at each individual stage of the FDE cycle. So it could be a fill in the blank. It could literally just be what are they doing what are the registers doing at the fetch stage of the FDE cycle. So I've tried to list it and number it for you. Address is copied from the PC to the MAR. Again, no inference that the program counter is doing it, like that. The instruction held in the address is copied to the MDR. This will help you with some of the points on the previous one as well. Simultaneously, probably don't need the word simultaneously, make it easier for yourself, give yourself less. The contents of the program counter are incremented, less to remember, more likely to remember it. The contents of the MDR are copied to the current instruction register. So that's the fetch stage. Decode stage. Decode stage is the instruction held in the CIR is decoded. It's split into operand and opcode to determine the type of instruction. Additional data, if required, is fetched from memory. We'll get rid of the if required. I'm always trying to give you as little as possible to remember, and passed to the accumulator. Execute. Control unit carries out the instruction, sending it to the ALU. Results stored in the accumulator. ACC is just an acronym, and you can use the acronyms to describe them as well. So fetch, decode, execute. Know that off by heart. State and describe a method in which the CPU performance can be improved. I've put 2 on here, and then on the next slide I've put the other 2. So clock speed is one of the first ones. You can increase the CPU speed by increasing the clock speed. The clock speed is, so if you have a 3 gigahertz processor, that means about 3 billion fetch, decode, execute cycles happen per second. So the higher that is, the quicker the computer is. A computer core, so number of cores, if it has more cores, generally this is going to be it's going to be faster. This is because it can work on different things simultaneously. We're going to have a look at pipelining in a second and what that means. And essentially what this is if you have multiple cores, you can do something called parallel processing, which just means you can do things all at the same time. Cache is another one. So it's the same question. I'm just putting all of the points on there. Cache is essentially a little memory store in just within the CPU, and it just means that the larger that is, you don't have to go to RAM to fetch anything. So it stores frequently used instructions. So the less you have to go to RAM, it's going to shorten that space. Then it's going to simplify the whole process. Pipelining is one that you won't have heard at GCSE, but pipelining is a one which is every core is doing a different part of the fetch, decode, execute cycle. So it's this idea that one core is fetching, while the other core is decoding, and the other is executing. So, and you need to say it in that way. So one core is fetching while the other is decoding and the other is executing. And this allows for parallel processing. And all 3 of that, it's normally a 3-mark question. You get 3 marks there. Very quickly, what they might get you to do is they might just get you to calculate which is going to be the faster one and why. So you've got a gigahertz, this one over here, 1 gigahertz, and you've got 4 cores, 1.4 gigahertz, 2 cores, which is faster of why. Generally, ignore the cache. If they are the same, that could be like the tie break factor, if you get what I'm saying. So I'll explain that. 1 gigahertz is 1 gigahertz times the number of cores. So total clock speed is clock speed times the number of cores gives you total clock speed, which is 4 gigahertz. The other one is 1.4 times 2 equals 2.8 gigahertz. Comp 1 is going to be faster for the flight simulator in this case because it has a higher total clock speed. If they happen to be the same, and then you had the cache size, and that was the only deciding factor, then you might make a case and say like, well, they've got the same total clock speed, but the cache size is the same. The cache size is different, and this one is larger. That might be the sort of tie break between the 2 of them. Embedded systems, the definition for this, if they just ask you like what an embedded system is, within a computer system within a larger system with one purpose: fridge, microwave. An embedded system. They may also say like, what is an embedded system in a particular situation? I've used a car parking system, GPS, automatic windows. The alternative to that is a general purpose computer, and a general purpose computer is what you're using right now, I would suspect, which can perform multiple tasks on multiple purposes, e.g. desktop computer, all that stuff. Linking that back to von Neumann and Harvard architectures, generally von Neumann is general purpose computers. Embedded systems are Harvard architecture. Okay, so we've got that one. Okay, right. So now going on to primary storage, and I think the definition is actually changed on this. So I'm just going to leave it to that. I'm going to take those two out on that one. So give an example of primary storage. It's a piece of memory that is directly connected to the CPU, which is RAM and ROM. For a while, I remember that they did use, I think it was in like maybe 2018. Anyway, you don't want a history lesson on it. Essentially, they use cache and registers, but I think they've changed that now. So I'm going to leave it out because I don't want to take any risks. We're just going to say RAM and ROM because we definitely know that. Sometimes the definitions change with what people are giving marks for and stuff like that. So let's go with that and not take any chances. Secondary storage is the idea of non-volatile permanent storage for files and applications when not in use by the computer. The concept, if you just remember the definition, great, that's the kind of first step. But the understanding of this is, when I want to use something, I load it from secondary storage, which is when it's almost like dormant, and then I load it into RAM. Then what happens is I'm working on it. So right now, like my PowerPoint is working on it, and essentially what with that, I'm getting the data and instructions and everything from there, and it's that idea between the two of them. ROM has some really, really important programs and instructions on there, which we'll talk about more in a second. But yes, generally it's the idea that you go from secondary storage when not in use. RAM, we load it into RAM and we start doing stuff on it, and then when we don't want to use it, it goes back into secondary storage. They do sometimes get you to compare the RAM and ROM. I was doing some questions with a student the other day, and did have this. RAM stores instructions and data that are currently in use by the by the computer. It also stores the operating system, which is in use by the computer. ROM stores the BIOS and bootloader. The BIOS and bootloader are some of the most important programs on the whole computer. We do not want these to be changed. We do not want these to be edited, because when you turn the computer on, the bootloader is the program which essentially loads the operating system into RAM, essentially turning the computer on. So this is one of the most important programs on the whole computer, which is why ROM is read-only. RAM is read and write, which essentially just means that you can change stuff on it, which makes sense because it's the stuff that we're using in this particular moment in time. ROM is just read only. We can just read it because when we turn the computer on, that's what we want to do. What does it store? So we've kind of talked about that already on those ones. The other sort of, if they ask you to compare them, RAM is what's called volatile. When you turn the computer off, it doesn't remember anything on it. ROM is non-volatile, which is when you turn the computer off, you still want to be able to have all of the things on there, because if it forgets the BIOS and bootloader, we could never turn the computer back on again. State the purpose of ROM, kind of already done that there, but I guess that's just not putting it on a table. So I'm going to skip that. Talked about volatile and non-volatile already on the previous one, so I'm going to skip that as well. If you want to make flashcards on those, I'll just leave it up there. Leave it on there. There you go. Okay. Virtual memory. Virtual memory is it's essentially where we run out of RAM. The computer can either crash, or what can happen is it can actually use virtual memory. Virtual memory is where we use part of our hard drive and we use it as RAM because we've run out of space. Now, the idea, which I guess is probably a little bit more of a you might want to add on there is linking this to the operating systems unit, which unfortunately I don't think I'm going to have time to put out a lesson before paper 1, so I'll tell you about it now. One of the jobs that the operating system does, so let's say that you get a question which is operating systems, and it will ask you to describe some of the jobs that the OS does. User interface, definition to use on that one is hides the complexity of the hardware from the user. And then you can, if you need to give an example, graphical user interface, command line interface. But the other one that you can talk about is memory management, and you can use and say, like, it does memory management, and it does this thing called paging, which is where it's essentially puts data into chunks, and what it does is it loads these pages into so from RAM into the CPU, and these pages have to be what's called contiguous. Tying this together with virtual memory, one of the jobs of the operating system is actually to, when we run out of RAM, is to use virtual memory. And if you talk about that in there, so if you get a question where it's like, name a job of the OS, and you can go memory management, you can say, oh, it creates pages, and the other one is segmentation. And it also does the virtual memory, which is when the hard drive, when the RAM runs out of space, that it uses part of the hard drive uses part of the hard drive and as RAM. And what it does is it loads things from the hard drive into RAM so that it can be used by the CPU. Now, the advantages of this is it's virtual memory stops the computer from crashing. Big advantage. The bad thing is, though, is it's very slow, and it creates this thing called disk thrashing, which is where the whole process and everything just slows down, and it's it's just a lot slower. So that's the kind of main thing. And if you use the key term disk thrashing as well, that would give you a mark just for that as well. So that's virtual memory. Okay, secondary storage. We gave a definition for secondary storage already, but the three main types is that you've got solid state, magnetic, and optical. Now, with these, so this one is optical, and you also got to know how to describe how it works. Don't know why we still do about CDs and DVDs, because they kind of, no one really uses them that much anymore. But anyway, examples of CDs and DVDs. If it asks you about a scenario and you need to give some kind of advantages and disadvantages about this, quick advantage is CDs are portable, but the main problem is they get scratched really easily and they're easy to damage. So optical, first mark, disc spins and laser is shot at the disc. Okay, so disc spin 1 mark, laser is shot at the disc is 2nd mark. So yeah, you get those. There are these things called pits and lands, which go out a spiral from the middle. So 3rd mark. The laser reflection is measured when it passed over the pits and lands. 4th mark. It then determines whether it is a 1 or a 0 based on whether it goes over the pit or the land. So 5 marks there. If it's 4 marks, then you don't need to put as much. Hard disk drive. I always try and make it as simple as possible for you to remember. HDD has a disk which spins, so same as the CD. So HDD is an example of magnetic storage, by the way. Disk is split up into tracks and sectors. A read and write head passes over the different areas and reads whether the data is a 0 or 1. I would actually also add on there that how it does that is it has magnetized particles, and whether these particles are magnetized or not magnetized is the thing that determines whether it is a 1 or a 0. If they give you a situation where they're asking you for your recommendation of whether you would use this, I have seen this one situation where generally you use solid state in every situation, which we're going to talk about. But say if there was like a budget constraint and there was a company that maybe didn't have as much money, and it was maybe trying to do something for like backups in the evening, where speed, like, even though HDDs, like, they have actually quite quick write speeds, not as fast as solid state, but it's not absolutely essential that you have to do everything as fast as possible, and it's cheaper than solid state. You could use magnetic storage as a backup. So that would just be the one situation which I just thought I'd draw your attention to on that one. I think I skipped one. Yeah, okay, so solid state. Solid state works by having an electrical charge that is either trapped or not trapped by NAND gates. If it's trapped, it's a 1. If it's not trapped, it's a 0. And then this is red. So you'd always, with every single one, just make sure that you know how to describe whether it's a 1 or a 0. Examples of this is SD, USB, solid state. Advantages: it's portable, has the quickest read and write speeds. The only real disadvantage is that it is slightly more expensive than the others. Just in case you get a question about cloud storage. Now, weirdly, they called cloud storage, I think this was on OCR, maybe on AQA as well. They called cloud storage virtual storage for a while. I don't know whether they've changed that now. And I think they may have changed that because of the confusion with virtual memory and virtual storage. Like, they sound kind of the same thing. So just be careful of that one, because if they kind of, like, in the question, they seem like they're talking about virtual storage, and it seems like they're referring to clouds, or, like, you know, people working in other places. They're talking about cloud storage, so just careful on that one. Cloud storage is where the storage is not held on the actual device, but in a remote server in another location. It requires an internet connection. The advantages of this, just quick ones: can access files from any device as long as you have internet. Easier to collaborate with other people. Negatives, though, is has to have an internet connection to access it, and you are trusting a third party with the security of your files. Whilst the security, I'm sure, is very, very good, we are trusting people that they're going to be good. Couple of little input and output devices. I was having a quick look at the ones which I thought maybe were a little bit not so obvious. Barcode readers. The way it works is it reads the thickness of the line. So you've got guard bars, which are just almost like, I guess, almost like the quotation marks around when you're writing in a print statement in Python. It's like saying, like, this is the area you're going to look at. The light shines on the barcode, and that then can measure the thickness of it, and then that turns it into a number, which will be an equivalent to, for example, in this case, a banana, and then other little extra bit that you have to put in there. That then is linked to a database which will subtract 1 from there and say that you have 1 less quantity in stock. So shine a light on there. So you shine the light, that measures the thickness of the lines, that then links to a database. The database subtracts 1 from there. Sometimes they sort of ask, like, how does it automatically, like, reorder stuff? So you would say when it gets to a certain quantity in the database of numbers in stock, it automatically reorders that from there. So I just thought about barcodes there. Digital cameras break up what it sees into a grid of pixels. The shutter opens to let light in onto the sensor at the back of the lens. The intensity of the color of the light is measured by the tiny sensors of each of the different pixels. Laser printers, they use something called toner. Don't use liquid ink. It uses an electrostatic charge to produce text and images on paper. Generally, laser printers, they use that over inkjet printers for large numbers. So that's why schools, organizations use laser printers, because if you need to do 100 copies of something, it does it really, really quickly, because it does it the whole document. For 1 or 2 copies, it's actually quicker to use an inkjet printer, which is just probably the one that, if you have a printer at home, it's got that one there. Okay, so that is going to be everything for AQA.